Hello, I will talk you through some of the results of our paper, Long-Term Variability and Debris Transiting White Dwarfs. Before going into the details, I'll start off with the solar system. In the solar system, we have 4 rocky planets going around the Sun. That's Mercury, Venus, the Earth, and Mars. Then we have a gap where there are asteroids, rocky bodies, small rocky bodies, but they're not all that small. Some of them can be a few hundred kilometers in size. And then we have the 4 gas giants further out in the solar system. Now, what happens to the solar system in the future? Currently, the Sun is burning hydrogen in its core, and once the hydrogen is used up, the Sun will start to expand. It becomes a red giant. And as it expands, it will engulf and burn up Mercury and Venus, and possibly the Earth. Now, while the Sun is growing into a giant, it loses mass. It will lose about half of its mass in total, and that means as its gravity weakens, everything that goes around it will slowly spiral further out. And so everything that survives the evolution of the Sun will move out by about a factor 2. What about the Earth? We don't really know exactly what happens to the Earth because we don't exactly know how much mass is lost at what point in the evolution of the Sun. So whether or not the Earth can just move out fast enough before the Sun can catch up and burn it is not clear. But whatever, the Earth will lose its atmosphere and its ocean and will not be a very nice place to live on. Okay, so in the future, 5 billion years from now, the Sun will contain a white dwarf in the center, and it will have at least one rocky planet going around it, Mars, and asteroids and the giant planets further out. Now, we know lots of white dwarfs in the galaxy. They may have had planets in the past, and many of them still have planetary systems today. What will happen in those systems? So we expect that they have a mixture of rocky planets, maybe asteroids, some moons, and giant planets. Every now and then one of those giant planets, because it has a larger gravity than the smaller bodies, will nudge one of the smaller bodies to move onto a trajectory which brings it very close to the white dwarf. And the white dwarf has a very high gravity near its surface. So the tidal forces as that body comes close to the white dwarf will tear it apart, shred it into debris. And that is exactly what we study in this paper. We studied using high-speed photometry obtained with a special camera at a telescope in Thailand and monitoring surveys obtained with small telescopes around the world, the variability of white dwarfs on timescales of minutes and out through to decades. Okay, so what happens if the orbit is aligned in such a way that the debris that passes in front of the white dwarf crosses our line of sight? In that case, the white dwarf will dim by some small amount, just similar to the transits of exoplanets that cross the line of sight of their host stars. However, the debris is much more fine structured. It's not like a nice round shape of a planet. And so using our high-speed photometry, we have observed one system where we knew that debris is transiting regularly every 4.5 hours, to see how those transits develop over the last almost 10 years. And what we found is that in 2015, the transits were very irregular and deep and recurrent. So with time, the transit depth and shape and the number of transits has decreased to a degree where today there's hardly any activity seen in the white dwarfs. And that means the evolution of the debris around white dwarfs is highly complex and changes with time. In a second system which we studied, where transits have been only found 2 years ago, and the material is going around with a period of 9.9 hours, we went back using the photometric surveys, and we found that around 2012 the system faded overall, and it stayed dimmer by quite a number of years. So what we think is that back then there must have been a catastrophic event, a collision, maybe between different bodies, maybe the disruption of a single body, that created a large amount of dust and gas, which overall blocked light of the white dwarf, leading it to be fainter than it was before. And it has since then slowly recovered in brightness, not quite to the level that it had at the very earliest observations. And we think what we see there was the catastrophic process that led to the debris that we detect orbiting the white dwarf today. And then a third system that we studied is the strangest of all, because every couple of months it dims for maybe a week, maybe 2, and then recovers in brightness. And then another dimming event follows a few months later. However, we have not been able to determine any periodicity, any periodic orbit of the material going around the white dwarf. So what we imagine is that we have clouds of debris with fragments of different sizes that pass in front of the white dwarf on a highly eccentric orbit. And then nothing happens for a while until the next cloud passes in front of the white dwarf. And that material goes around on a very eccentric orbit and will come back eventually. So we will keep studying that star, and we'll hopefully, with time passing, we'll be able to determine on what period the material goes around it. So in summary, using a combination of high-speed photometry obtained with a special camera in Thailand and the long-term monitoring with small telescopes placed around the world, we have shown that the evolution of material rocky bodies entering into the gravitational field of the white dwarf, being torn apart by that gravity, is extremely complex, extremely variable, and we hope that our results will help theorists developing a better model for the what we call tidal disruption of these bodies, and we will of course carry on these observations to get a deeper understanding of how these three systems evolve in time into the future.